and welcome back to my garage. In the last video I mentioned the idea of density, that water can have different densities and that changes the amount of buoyancy that you can get from it. And I said I would come back and I would demonstrate a little bit more to do with the idea of density. Density is an incredibly important concept, not just in naval architecture but in any sort of field which involves building things, which involves, I mean, it's so broad that I can't even express to you how important it is. The basic concept is that some substances, not objects made of those substances, but just the substances themselves, are heavier than others. We all know this because of our experience throughout our lives. We know, for example, that oil is lighter than water, and this is why oil will always float on top of water. We know that muscle is heavier than fat, or so you will have heard if you know of anybody who has put on a little bit of weight and wants to find a reason for it other than the pizza that they ate. Possibly they want to believe that the weight was put on because they walked 5 minutes to the pizza shop in order to get the pizza, and so therefore they built up muscle, and muscle's heavier than fat. It's true. We know that gold is very heavy, and if you're familiar with the story of Archimedes and the King's Crown, you'll know that gold is significantly heavier than silver, and that was how Archimedes solved that problem. If you don't know that story, look it up and find it out. And this concept is, as I say, not the idea that just a lump of gold is heavier than something else, but the idea that gold itself is heavier, so that even if you have the same volume of gold and silver, the gold will weigh more. And the basic idea is that some substances just have more matter in them. The matter is more crushed together, it's more compressed, there's less space in there, and therefore that if you have the same volume, that substance will weigh more. And this is just so useful and so important to know. For example, that if you want to build something like an aeroplane, I don't know if you ever built model aeroplanes when you were a child. If you did, you know that there are certain materials that you use for that and certain materials that you don't. Balsa wood, for example, is often used for building model aeroplanes. So is polystyrene. The reason being that these materials have very, very, very low density, meaning that you can make a structure that's very, very light. Aluminium has a much lower density than steel. So if you're trying to build a commercial aircraft, you won't build it out of steel. Aluminium will be one of your number one choices because it's so very light, has such a low density, that you can make a structure out of it which is much lighter than it would be if you made it out of steel. And for that reason, high-speed ships are often built out of aluminium rather than steel, in order to take advantage of that low density. And in naval architecture, density is particularly important. Last time we talked about buoyancy, and we saw how as you place an object into water, it displaces a certain amount of water, and that weight of water that it displaces pushes back and provides the equal amount of buoyancy. Well, the heavier the water is, the more buoyancy it will produce. So if you have water which is more dense, then you will get more buoyancy back from it. And as a result, the object that you immerse in that water will be pushed out further. And perhaps even an object which might not float in the low density water may float in the higher density water. So I just want to show you this in real life. So I've got here are 2 tubs of water. And you saw me fill these up. They've each got 1 litre of water in them. And it's just ordinary fresh water out the tap. It's a little bit warmed up. But other than that, there's nothing unusual about it. And in front of these tubs we have this little boat, which you're familiar with, the small ship from the last demonstration. And it has still got these draft marks on the side of it, marked in centimetres. And we know from the previous demonstration that when it has no load on board, this little boat floats at a draft of around 2 centimetres. So pop it in this tub here, and you'll see it settling down to that draft. And you would also see the water level in the tub pop up a little bit, because the tub is small enough that you can actually see the water displacing as the boat goes into it. And the other tub, just to demonstrate, is exactly the same. Pop our boat into it, and it floats down at its draft of about 2 centimetres. Now, if I were to want to increase the density of the water in one of these tubs, there's only really one way I can do that, and that is to dissolve something into it so that there is more mass per unit volume in that water, because there's not just the water there's something else dissolved through it, so there are extra molecules distributed through it. And there's various things I could put in. Sugar's a good one. If I put sugar in, sugar's quite heavy and it dissolves in water quite readily, so if I put sugar in, then it would make the water heavier. But another item that I would put in, which might be a little bit more sort of normal in real life, is salt. As you know, the sea is salty, and that causes the sea to have greater density than fresh water does. I'm not going to add just enough water to turn this into a seawater type brine, because the difference in the draft on the wee boat would be too small for you to see if I did that. So instead what I've got is I've got enough salt to turn this into effectively the Dead Sea. So let's just see that. So for this litre of water here, I have got 250 grams, that's a quarter of a kilogram of salt. And as you'll see as I put this in, it's quite a lot of salt. The reason I warmed the water up a little bit was to make dissolving the salt in it a little bit easier. As you'll know if you've ever tried to sweeten iced coffee, salt and sugar do not dissolve well in cold liquids. However, it still takes a little bit of stirring. Okay, we're there. Now, if you have a look at the boat in the freshwater tub, if I push it right up to the side there, you can see that draft just a little bit more than 2 centimetres, but not much. That's the approximate draft. So let's have a look at where this boat would float in the Dead Sea. Oops. But watch that meniscus. If I push it right against the side, you'll see that the water starts to suck up between the boat and the side of the tank. That's another fascinating thing about water. The meniscus and the capillary action. You can see that the draft has changed so that it is closer to 1 3/4 centimetres rather than the just over 2 that it was in the freshwater. So if you imagine that on a full-sized ship, the difference between the freshwater and the Dead Sea water is really, really significant. If you were to take a vessel from freshwater or from the sea, which is more dense in freshwater but significantly less dense than this, that vessel, when you brought it to the Dead Sea, would float quite a lot higher. And it would be necessary to put some ballast in it, because otherwise you might actually be in danger of a boat that was designed to float in freshwater or normal seawater becoming unstable in the Dead Sea because it's floating so high. So the Dead Sea is a very extreme example. If you've ever been there, you would know that. Have a wee Google of photographs of people floating in the Dead Sea, and it is quite a sight. They do float a lot higher than they would in freshwater or normal salt water. But even the difference between freshwater and seawater, it might seem insignificant to you. So freshwater has a density of 1 tonne per cubic metre, and so seawater has a density at most of 1.025 tonnes per cubic metre. And that might seem like a negligible difference to you, but actually for a full-size ship, it can be a difference which can actually make a real difference to its safety. It's very, very important for a ship to have enough freeboard. So the freeboard is the distance from the deck edge to the water. And the higher it floats in the water, so the less draft it has, the greater its freeboard. So you can see that this boat has a greater freeboard when floating in the Dead Sea than it does when floating in the normal fresh water. And what that means is that a ship which is safe in this situation because of having enough freeboard may not be safe in this situation because its freeboard is much less. Similarly, a ship which is safe in this situation because its stability has been designed for that may find that it does not have enough stability moving into this situation. And you get a similar issue moving between freshwater and seawater, although it's much less exaggerated. And so what we do for ships which might at any point in their life move between fresh and seawater is we mark on the side of them what the difference would be in the draft if it was moving in between fresh and salt water. And that's called its freshwater allowance. And it's a really important thing that has to be taken into account in all the ship's calculations. So if I was to do what we wanted to do in the previous demonstration and weigh this boat by calculating its volume under the water, it looks a little bit like that volume changes. When you're in the fresh water, it's floating at a draft of 2 centimetres or just over, and therefore it's got apparently a larger volume under the water than it does when I put it in the salt water. And yes, it does. It does have a larger volume displacement in the salt water, in the fresh water, than it does in the salt water. However, it has the same mass displacement. Remember the mass displacement, the mass of water that the vessel displaces is the same as its own mass. So I can't change the mass displacement of this boat unless I add something to it or take something away. So the difference is caused by the fact that there's a different density. So if I calculate a volume displacement here and it's smaller, volume displacement here and it's larger, but if I multiply this volume displacement by the density of 1 tonne per cubic metre, and I multiply this volume displacement by the density of, it's about 1.24, 1.25 for this Dead Sea water, tonnes per cubic metre, I will come to the exact same mass displacement. So I hope that has helped with understanding density and how it works. So go away and have a look at some videos and pictures of the Dead Sea. Enjoy looking at that. It's a really unusual situation where the water has become so salty due to having so many rivers flowing into it and none flowing out, that it's about as salty as it physically could be. The salt on the Dead Sea starts to crystallise on the rocks round about, and there's pretty much no life in it because of the amount of salt that's in there. So there's no other water on Earth naturally which is saltier than that, as far as I'm aware, in a large body of water like that. But that difference, that extreme situation illustrates something which is important just in considering the difference between a lake and the sea when you're designing a ship. Hello, there's just one more thing that I want to add to all that. If you remember back to the previous video, you'll remember that we measured it would be tonnes per centimetre immersion on a full-size ship, but we measured how many grams would make our ship sink by a centimetre. And the question that I want you to be asking yourself just now is, if the water is more dense, does that change the tonnes per centimetre, the TPC as we call it for short? And the easiest way to answer that question is with a demonstration. So I'm going to do that. So we've got our boat, and we'll remember that in fresh water it took 149 grams to sink this boat by a centimetre. So it's currently floating at about 1 3/4 centimetres. So let's see how much weight it takes to get it down to 2 3/4. Okay, so we're not quite level, we have to be level. So what's that at? That's got us to just over 2. Two. water. Oh, it's not level. Still not level. Water. 2.5. I may have to do some jiggery pokery here because I've had this big one. I think it's going to take it over what we want. I think I have to take the tiniest one back out again. And do a little bit of balancing. I've got them tangled up. No, that's taking it too low. Let's see what happens. See, that's a little bit too much. No, we're not balanced. Leaning to one side there. That's about right. So let's measure how much weight that is. Sharpie, and we've got wee spanners. 179. So it takes 179 grams to sink this boat by a centimetre in this Dead Sea water, and 149 in the fresh water. And you unfortunately aren't here, so you can't feel this effect, but if you actually play with this boat in this water, push it down, you can feel the extra buoyancy. It is just an awful lot more prone to float in this water than it is in this water. And it changes its whole behaviour. And it's quite a fun experiment actually if you have a bit of salt to spare. Try this yourself. So to a litre of water, 250 grams of salt. Warm your water up a little bit. It's only about 40-50 degrees. It's not very hot. And then stir the salt in and get something that floats and transfer it between the two, and you'll feel a real difference in how it floats, and we see that reflected in its grams per centimetre immersion. And so on a full size ship, yes, it will have a larger tons per centimetre immersion in a more dense water. Okay, see you next time.